SwayamPrabha. Digital India. Educated India.
In the last class, we were working on some part of energy and energy transfer. We started with the first law of thermodynamics. Now, we will continue with the discussion, and in this lecture, we are going to talk the energy conversion efficiency. This is something quite relevant for our daily life when we look at any devices, whether it's a refrigerator, whether it's a oven, okay, whether you're buying a bike or car, you look at efficiency, like how efficient the device is or the machine is. And one of the daily usage at our home is a water heater. So we'll go through different aspects of this different devices and its their efficiency. But let us first define what is efficiency. And this is a generic term. It is not a term relevant only to engineering, but our other daily life activities. So efficiency is nothing but the ratio of the desired output and required input. Now this desired output and required input would be different for different contexts. In case of thermodynamics, is always related to some form of energy. So let's take the different kind of water heater. What you have typically in that home, the efficiency is defined as the ratio of the energy delivered to the house by hot water to the energy supplied to the water heater. So whatever the water being heated up, like how much energy it contains, what you use it, that divided by the energy supplied to the water heater. So it's a simple ratio. The issue is that how do you compare with other systems? So because it's not always the electrical based heater, it could be gas based heater, it could be some other form of heater, and the efficiency vary. So how do you really compare? So this efficiency, for example, gas is quite lower compared to the conventional electric base, very high. Okay, the loss is quite limited. And when you go to the market and you talk about it, and you always get confused because these guys, some guys will say it's very high efficiency. You don't know what they are using it. If you are aware of it, then you can quantify and you can calculate its cost. And cost does vary a lot. Okay, so let's look at why the gas-based water heater has a low efficiency. Okay, the reason being that this efficiency is being calculated based on the combustion of a fuel. Okay, and that is related to heating value of the fuel. So what is the heating value of the fuel? Is the amount of heat released when a unit amount of fuel at room temperature is completely burned and the combustion products are cooled to the room temperature. This is an example of a combustion chamber. You have air which passed through, and let's say gasoline which is passed here. It burns, and after the burning, the gases, the combustion gases consist of CO2, H2O, N2, etc. H2O is in the vapor state, and thus this is an example of low heating value. It says that when the water leaves as a vapor, the energy associated of this combustion would be low heating value. The reason being, water takes a lot of energy out of it. You're heating it, water comes as a vapor, it contains a lot of energy, hence whatever is useful energy remains is going to be of low quality. Okay, but when you condense this water vapor and then you use this heat of vaporization as a part of your output, desired output, then the corresponding heating value would be higher heating value. Okay, so when the water in the combustion gas is completely condensed, the heat of vaporization is also recovered in such case. High heating value. Okay, so how we define this combustion efficiency? Amount of heat released during combustion divided by heat value of the fuel burned. So that's a ratio. So it's like Q divided by HV. So this HV could be HHV, higher heating value, or LHV, depending on what is the state of the combustion gas. So let's further look into more efficiency. What about generator? So a generator is a device that converts mechanical energy to electrical energy. It gets a shaft work, okay, output from the turbine and converts that into electrical energy. And how are you going to define the efficiency of a generator? It's a ratio of electrical power output to the mechanical power input. And what about the thermal efficiency of a power plant? So it's a ratio of the net shaft work output to the heat input to the working fluid. So in a power plant, it's like the thermal efficiency is related to the turbine, okay, because you've already heated the water and the steam is given to as an input to the turbine, and turbine high pressure, it expands, this steam goes to the low pressure. While doing this process, it actually generates a work. So what is the thermal efficiency of power plant? It's the ratio of the net shaft work output to the heat input to the working fluid. So when you consider the power plant as a whole, you have to take different components and their efficiency, and you multiply them. So the overall efficiency would be the net electrical power output, because that is a desired output of the whole power plant, to the rate of the fuel energy input. In this case, you are going to burn the fuel, use that energy to heat up the water, convert to steam, and steam is used to do the work through turbine. So this whole cycle, you have to consider the combustion chamber, you have to consider the turbine, you have to consider the generator, all three of them. So this is going to be the overall efficiency, eta combustion, eta thermal, and efficiency of generator. You can make use of definition of each of them. For example, here, what is the combustion? This would be Q out divided by the heating value. But now we are going to multiply M also, because heating value is typically per unit mass. So we are going to multiply by M. So that becomes the combustion efficiency. What about the thermal? As I already mentioned, thermal is a net shaft work output. So that will be shaft out divided by Q in. Okay. Q in is basically same as Q out. Okay. And eta generator would be net out, which is electrical power output, divided by the mech in, mechanical energy, which we are using here. So this you can write all of them in a rate form, converting into the power. So this effectively should give you this, because this should cancel if it is a perfect conversion, and effectively you can write this, that this is our net input. So W net electric would be the desired output, and this is desired input. So take an example of some common case appliances. This is an example of simple appliance. So you are using this device, okay, which is using electrical power, cooking appliance here, which is simply a utensil having some fluid. So it's 5 kilowatt you have taken from the electrical point, and it's only 3 kilowatt is being transferred. So thus the efficiency of this particular appliance is 0.6. And similarly, you can come up with a different kind of cooking appliances, okay, and which may be based on electric, based on gas, and based on other forms. And this is a summary of these appliances, the cost of the energy used based on United States data, and you can clearly see that some are extremely small compared to others. The cost being low doesn't mean means efficient, okay, and it also doesn't mean it is you getting a good food, for example, if you are related to the food. I mean, so but otherwise, it's important to be aware of the energy efficient appliance, because at the end, if you are using a high efficient appliance, you are conserving the energy in some form. And if you can reduce the combustion of fuel by any mean, is going to help the environment, because the combustion of fuel produces various different gases such as carbon dioxide, which causes global warming, nitrogen oxide and hydrocarbons, which cause smog, carbon monoxide, which is toxic, and sulfur dioxide, which cause acid rain. Thus, if we are using energy efficient, even if it's little higher cost, is good for the environment. Now, as an engineer, you need to develop this kind of highest or higher energy efficient devices, and that's of course the challenge. Okay, that's also the challenge for power plants, for other in the petroleum industry, to increase the output, desired output, with lower possible input. Okay. Now we'll continue with the discussion of efficiency of mechanical and electrical devices. Now any transfer of mechanical energy is usually accompanied by rotation of shaft, and thus typically the mechanical energy is often referred as shaft work. So imagine again the mechanical energy of the fluid in your dam, you transferring the mechanic in some form of turbine shaft work. So this is a popular thing, or pump for example, okay. That is also mechanical transfer the mechanical energy or from the motor it transfer to the fluid in some form. Okay. So let's take an example again of pump and turbine. A pump or fan receives shaft work usually from an electrical motor, and the job is to transfer it to fluid as mechanical energy. So the pump is used to increase the pressure, and thus so it's increase the mechanical energy, because mechanical energy has a pressure head, the pressure component, pressure energy or the flow energy P by rho. A turbine converts the mechanical energy of a fluid to a shaft work. This is simply a mechanical energy output divided by mechanical energy input. You can write this in this form, E mech out divided by E mech in, and also in this form where this is nothing but 1 minus E mech loss divided by E mech in. If the loss is close to 0, then you will get almost 100% conversion. So you can convert a mechanical form to another mechanical form theoretically 100%. So further we can look little more detail for the case of pump and turbine. So what's the job of a pump is to increase the pressure, okay, and that is the pump can do that, the fan or compressor also can increase the pressure of the system, and that means it increases the mechanical energy of the system. So this is the if you want to find out the efficiency of pump, that will be the ratio of mechanical energy increase of the fluid divided by mechanical energy input. So what is the input in this case is W shaft in for the pump, and what is the output? So it's mechanical energy increase of the fluid, and that we are going to say as W E mech fluid. Okay, we are using dot because it's a rate based, so it's basically a power mode, and this is equivalent to a useful pumping power for pump. Okay, that's why this U stand for it means useful. So what is the change in the mechanical energy of fluid is simply E mech out minus E mech in. So remember, for the pump E mech out is greater than E mech in because it is already increased. So what about the turbine? The turbine job is to extract mechanical energy of the fluid, because turbine the fluid expands, the pressure drops. So it basically it extracts the mechanical energy of the fluid. In that case, the way we are going to define the efficiency of turbine is mechanical energy output divided by mechanical energy decrease of the fluid. Now this is a positive value, and thus we are going to use here the absolute value of delta E mech. Okay, so and this E stand for again is extract. We are trying to extract the mechanical energy of the fluid. That's why we are going to use this absolute value in this form, E mech in minus E mech out. So remember, this is little different from the pump. Pump we used E mech out minus E mech in because it was all like E mech out was greater than E mech in. In this case, E mech in is more than E mech out. So once you do this absolute value, we are using the absolute value of this decrease in the mechanical energy of the fluid. So let's take an example. So this is a fan, and fan uses a shaft work of 50 watt, and then the air here has the mass rate is given is 0.5 kilojoules per second, and we need to find the mechanical efficiency of this fan. So how are we going to do that? We are going to use the expression what we have used for pump, delta E mech fluid divided by W shaft in, because here there is no, the air is stationary. Okay, this is stationary, which means that the velocities will be 0 here. Here the velocity is given as 12 meter per second. There is no change in the elevation, there is no change in the pressure. So the mechanical energy of the fluid will have only the kinetic energy part. There is no change in the pressure part because there is no delta P by rho, and there is no delta PE. The only thing which we have is delta K. So this is going to be 0, this is going to be 0, and thus you have only this kinetic energy, and that's what you're going to use. Okay, and the shaft work is already given to you as 50 watt. So you replace this value, and this turns out to be 0.72. Okay, so many times we are interested in the combined effect. So for example, motor is connected to your pump, or generator has a turbine. So having just efficiency of a turbine is not sufficient. You are interested in the combo or combination of both the things. So as mechanical efficiency should not be just confused with a motor efficiency. It has a different definition. So motor efficiency here would be simply the ratio of the mechanical power output and electrical power output. Okay. On the other hand, your generator would be electrical power output divided by mechanical power input. So what about the combined pump motor efficiency? You are going to just multiply the individual efficiency. Or in other words, you can come up with this direct form where you are saying that pump and motor combined has the effect of increasing the mechanical energy of the fluid and is divided by the power it takes. Okay, and the effect is directly reflected on the mechanical energy of the fluid. Similarly, you can do that for turbine and generator. And so here the turbine and generator is given by the electrical power output divided by the decrease in the mechanical energy of the fluid. Okay, that is a turbine generator overall efficiency. So this is an example here. So this is a combination of a turbine and generator. Individual efficiencies are given. So turbine generator efficiency will be simply the multiplication of individual efficiency of turbine and generator. We will end this lecture by doing this energy analysis. Okay. So this is a turbine generator efficiency problem. Electrical power is to be generated by installing a hydraulic turbine generator. So this is the hydraulic turbine generator, which is at a site 70 meter below the free surface. The free surface is this, okay, of the larger reservoir. So this is the larger reservoir, this is the upstream, this is the downstream. So this will be downstream. So this is upstream. So a larger reservoir here. Okay. So it's saying that it should be installed at a site 70 meter below the free surface of the larger reservoir that can supply water at a steady state of 1500 kilogram per second, which means the m dot here, the fluid which is flowing out of it is 1500 kilogram per second. If the mechanical power output of the turbine is 800 and the electrical power generated is 750, which means this generator is generating 750 kilowatt of electrical power, then what is the turbine efficiency and the combined turbine generator efficiency? So that is the question which we have to solve. So we have to neglect the losses in the pipe. The first thing is we should write down the basic steps here. So let's say we are going to consider this as Z2, the point 2 which is written here, and Z1, and Z2 we are going to say it to be 0. Make this as a reference. So we know Z1 is 70 meter. So considering Z2 is 0, PE2 should be 0, right? These are stationary, there is no velocity. So the kinetic energy here should be 0, and same is the case for here. So the kinetic energy is of this point 1 is 0. Now what about the P1 and P2? We can assume these are both at atmosphere, right? Okay, so let us first calculate the delta E mechanical, change in the mechanical energy of the fluid. So what about delta E mech? So this will be m dot, because I am considering the rate here. This will be E mech in minus E mech out. Okay. Now since we know E is nothing but your P by rho plus PE plus KE, right? Now what about in here? And out is of course 2 and in is 1. So in this case E mechanical energy in is we are going to consider only the potential energy part. So this will be simply PE1, and this is going to be 0 because of the fact that PE2 is 0, KE2 is 0, and of course there is no flow energy. Okay. So this is nothing but m. So you have the information of change in mechanical energy of the fluid. Okay. So you can calculate what is PE is nothing but G times Z1, and so you can write the expression. So here is the expression finally. So this is the expression 1500 kilogram per second multiplied by PE. PE is calculated as G Z1, and this is the value which you are getting as change in mechanical energy of the system. Now remember that what I did was the absolute change. So this actually should be absolute change, okay, because I am using E in minus out. There is a drop in mechanical energy, okay, and that is what it is used, so absolute change here. Okay, so now once you have this information, how do you calculate your thermal efficiency? You can directly use the expression of what we have gone through. Thermal efficiency of turbine generator combination would be simply the electrical work output from the generator divided by the change in the mechanical energy of the fluid. Okay, that would be the combined effect of turbine and generator. So that turns out to be 72.7%. What about turbine? Turbine would be this should not be electrical, this should be shaft work. So because if you recall, the question had 800 was the mechanical power output, was nothing but shaft work. Okay. So this should be simply 800 kilowatt by 101. So that answer will be 77.6%. Okay. So what this reservoir does? So reservoir supplied 1031 kilowatt of mechanical energy, because that was a mechanical energy, to the turbine, which converts 800 kilowatt of it to a shaft work, and that drives the generator generating 750 kilowatt of electrical power. Remaining amount is lost. So this is how we are going to calculate and make use of efficiency to find out or solve such kind of problems. Okay, so let me summarize what we gone through in this module. We define the energy, define the macroscopic and microscopic energies. We also defined that energy can be transferred by heat, mass and work. Okay, these are different form of transfer of energy. Okay, and particularly heat and work will be recognized only at the boundary. We went through the first law of thermodynamics, went into the details, went to the expression, applied this particular expression or the analysis to a system, and eventually we ended this module with energy conversion efficiency and some examples. Okay. So that will be the end of this lecture. Next lecture we are going to go through the property of the fluid and we will understand the phase change and other aspect of it.